Right, so we were continuing our homework problems from my winter 13 Monday, Wednesday, Friday class for the homework that was due on 2/25. And we were going with our second problem, and we'd had outlined what each of these problems were asking us to do. So the first problem here is not an application of the central limit theorem. We're looking for a single random variable, which is normally distributed with this mean and this standard deviation, which means what I need to do is just standardize it based upon the given mean and the given standard deviation of the x's. So I'm going to start with x minus mu divided by sigma, and I'm going to standardize my x, 3,500, by subtracting the mean, which is 7,500, and then dividing by my standard deviation, which is 1750. Notice this is not the standard error, this is a single random variable. So this is going to give me the probability that a z is less than, and I have 3,500 minus 7,500, and then I'm going to divide that by 1750. And so the z-score that I get is a negative 2.29. And remember, I always want my students to round these off to 2 decimal places because I want to be consistent whether you're looking it up with a calculator or with a table. So this, remember, is a direct table lookup because this says I have the standard normal random variable. Here's a negative 2.29 represented on this table, or this chart, and that is the area that I want, which is exactly what a negative z table gives me. So I look over here for negative 2.2, and then I follow it all the way across to negative 2.29, and I get my probability being 1.0110. And so that'll be my probability. Now the second question, it changed, and it said now the doctor takes a sample a week apart. So I have 2 samples, and we want to know the probability that the average of these is less than 3,500. So this time around, my x bars are distributed normally because we know the original is normal, so the central limit theorem applies, with the mean of the original distribution and a standard error of the original standard deviation divided by the square root of the sample size, and the sample size this go around is 2. So we have the probability, and we have the x bar minus its mean, which is the same as it was before, divided by not just the standard deviation, but the standard error, which is standard deviation divided by the square root of n. So this time we have the same number we had really up here, the negative 2.29 with a few more decimals, and then it's going to get multiplied by the square root of 2 because we're going to have this 3,500 minus the 7,500, and then that's going to get divided by the 1750, just like it did before, but that gets divided by the square root of 2, and the denominator of the denominator is going to flip up and multiply by this thing here. So this is going to end up looking like the probability that a z is less than a negative, and we have the answer that we had before times the square root of 2, which ends up, if you don't accrue any round off here, being approximately a negative 2 or 3.23. And that's rounded off again to 2 decimal places. So you see now we've jumped this out way out here even further. And what's happening is because we're looking at a probability that's even further away from the mean, right? We're getting, because the sample size and the jitter goes down, this is even less likely than it was before. So this probability is less likely than when we were just looking at one value. So a negative 3.23, and that gives me this value right here. So now I have a probability of 0.0006. So the probability this time is smaller than it was the last time. Now finally, they've asked us to do it with a sample of size 3. So they take a sample once a week for 3 weeks, and then they find out what's the probability that the average is less than 3,500. So now again, the only thing that's going to change is this 2 is a 3. and we should see even less jitter. So we're going to see the same sort of thing, that our z is less than, and this one's going to be an even larger number. So we have 3,500 minus 7,500 divided by 1,750, and then we multiply that by the square root of 3. And that will give us our value this time around, which looks like a negative 3.96. So the way that I got this was exactly the same way that I got this one, except I had a 3 there instead of a 2. And so now this probability, again, right, this is just further out here in the tail, less jitter means it's less probable to be somewhere near the mean. So negative 3.9. So if it's lower than 3.5 in a table, the best you get is something that's less than, so this doesn't even apply, it's less than 0.0001. And if we actually do this in our calculator, we use the distributions menu and do the normal CDF, and I say that I want from negative infinity, so negative e to the 10th or so, up to negative 3.96, and I look for that probability. That probability is 0.00, so 4 zeros, and then 3749. And you see that's much less than 1/10,000th. And so that would be the probability that you would get from the normal CDF on your calculator. A very, very unlikely chance. So then the follow-up question on this says, all right, so now what happens? What's the interpretation? If you compare your answers for A, B, and C, how does that relate? So as n increased, what we saw is the probability decreases. And why it is decreasing is because the jitter, the average, right, being away from the mean, gets less and less likely the more samples we have. In a practical interpretation, if we had a patient that had 3 weeks of tests that are less than 3,500s for their white blood cell counts, then what we would say is that this person is very, very likely to have the indicators for leukopenia, which indicates that they have a viral infection of some sort, because it would be very unlikely we would see such results if it actually were not present, because the indicators have been there multiple times. All right, so the next question that we had in our homework, which I'll continue in another video again, we will be looking at this problem. Let X represent the dollar amount spent on supermarket impulse buying in a 10-minute unplanned shopping trip. And based on the Denver Post article, the mean of the X distribution is about $20, and the estimated standard deviation is about 7. So what we're told is that the X's are distributed some way, and it doesn't say that they're normally distributed, with a mean of 20 and a standard deviation of 7. And so now we're going to base our answers on that. So part A said if we consider a random sample of 100 customers, so n being greater than 30 means that we don't have to know that this is approximately normally distributed, and when that happens, then we know that the central limit theorem will apply, so the x bars will be normally distributed with a mean of 20 and a standard error of the standard deviation of this x divided by the square root of the sample size n. In this case, square root of 100 being 10, so 7/10 would be our standard error. Each of whom has 10 minutes of unplanned shopping time. That's the status for how we got the x's in the first place. And for the central limit theorem, what can you say about the probability distribution of the x bars? and the average amount spent by these customers due to impulse buying. What are the mean and the standard deviation of the X-bar distribution? Is it necessary to make any assumptions about the X distribution, and explain. So if we have a sample of size n, this being greater than 30, we have to make no assumptions based upon this. And that's because sample size of greater than 30, there does not have to be any assumption on the original distribution for the X bars to be assumed to have a normal distribution. So what we have is the X bars we will know to be normally distributed. Their mean will be the mean of the x's, and their standard deviation will be the standard deviation of the x's divided by the square root of the sample size. And that answers that entire question. And then the next one says, find the probability that x is between $18 and $22. So, or the average is between $18 and $22. So we're being asked to find what's the probability that if we have 100 shopping trips, that the average would be somewhere between 18 and 22. And then finally it says, let's assume the X distribution is approximately normal. What's the probability that the X's themselves are between $18 and $22? So the 18 and 22, that contains the mean, right? So with the sample means, we would expect there to be a much higher probability for the X bars to be within this range than we would for a single random variable. So this one we now assume to be normally distributed with the mean of 20 and a standard deviation of 7. So those would be the questions that we're going to answer, and then we'll talk about some interpretation.